Now, yesterday I mentioned to you, or the day before yesterday, Tuesday, I guess. I talked to you about what a battery, like a 9-volt battery looks like, but they refer to the battery as a capacitor. So what a capacitor is it has two conducting plates. One's positively charged, one's negatively charged. And then there's a material that's in between them. We refer to that material as dielectric material. Now, based on that type of material, it determines two things. Number one is it determines how readily or easily the charges flow from negative to positive, the electrons flow. And the second thing is it also determines whether or not the amount of capacity that it has to store some electric charges while they're inside that material. Now, we talk about capacitance. So capacitance is the ratio of charge on either plate compared to the potential difference. So capacitance right there is Q over V. Okay? Q represents the amount of charge on the plates. V is the amount of potential difference there is. So the potential difference we figured out the other day was the amount of work it would take to take one of these electric charges, the electrons, and transfer it over a given amount of distance. Okay, so the things that determine the ability of capacitance is the amount of charge, the potential difference, the type of material, and the size of the plates and the distance between the plates as to how easily the charges move from one to the other. Now, capacitance, we measure charge in coulombs, right? And we measure potential difference in volts. And 1 coulomb for every 1 volt is equivalent to the units for capacity, which is 1 farad. I put Faraday because that's the name of the dude, but it's farad. Okay? So the measure for capacitance is farads. And you calculate it by taking the ratio of the amount of charge over the amount of potential difference between the two plates. Okay? Now, the book will do a little bit of work on comparing capacitors, and there's a ratio that works for the amount of capacitors. So air is the original capacitor. So they have a dielectric constant, which is 1. All right. We compare all of our dielectric materials to air. So how many times greater does the capacitor work compared to air? Okay. So air has a value of 1. All the others are given to you on a chart on page 402. So you have paper, paraffin, polyethylene, polystyrene, hard rubber, mica, and glass. Those are all the types of dielectric materials that we're going to use. So a dielectric such as mica, which we use fairly often inside batteries, we'd have 6.0, which means it has a 6 times greater ability to store electric charge than what air would in a capacitor. Okay? That's all that means. Now, we won't do very much with it. There will be about 1 or 2 questions that we'll just ask you about changing the dielectric material. So what you do is you basically take whatever the capacitance is in C1 and you multiply it by your K value, and that will end up with the amount of capacitance that the second one has. Okay? It goes through the effects of dielectrics, which I don't want to read to you. Again, those are things that you can do when you answer your questions. But here's the last and most important thing that you need to take with you this year going into grade 12. So every battery has capacitance on it, it has an amount of charge on it, and it has a voltage on it. Okay? Now, my best analogy that I can use is to describe how we set these batteries up and what happens with electric currents is this. The old days, you'd take a string of Christmas lights, all right? You'd wrap it around your tree, do whatever, Christmas lights. One bulb would go out. It would all go
And
out.
the whole string.
The whole string is useless now, right?
Yeah.
So you would have to test every light to find out which one light burnt out because it cut off the circuit, right?
Mm-hmm.
So when we attach batteries and electric circuits, don't write this down just yet. When they are connected in series, okay? So I use this to describe batteries, capacitors, okay? That's what we call them. I refer to them always as batteries. They aren't, they're capacitors, which are similar to batteries. The charge acts like a current would in an electric circuit. Therefore, it has one way to flow. So if one of those batteries or one of those capacitors does not transfer the electrons, then the rest of them won't work either. Okay? And that's what happens in a strand of lights. Is once that circuit has been broken and the electric current can no longer flow through that one light bulb, it won't flow through any of them. All right? This is what we refer to as a circuit or a series of batteries connected in series. All right? And there's three things that you need to know about a connection in series. The first one is this. Now, this is important because when we get into electric circuits in grade 12, we'll talk about voltage, current, and resistance, and they have the same properties that I'm showing you here today. The same thing occurs in a series. The current is very similar to the charge, and of course, current comes from charges per second. So that's why they have the same properties. So the first thing that you want to know is the total charge in all three batteries don't change. They stay the same when connected in series. So the charge on one and the charge on the second and the charge on the third stay the same. I refer to it like the current in those light bulbs. As long as the current is flowing, it doesn't change. It stays the same because they're in series. Right. Okay? The second is the potential difference. The potential difference is the sum of all of the voltages on the batteries. So if I have a 9 volt, a 9 volt, and a 9 volt, I have 27 volts of potential when I connect them in series. Okay? So my voltage in series is the sum of all three. The capacitance, this one is a little different, but I'll make it make sense in a second. It's the sum of the ratios or the reciprocals of all the capacitors. Now, the same thing occurs for potential difference when we do, or sorry, resistance. Resistance when we do electric circuits. Now, these are the properties in series. And this is how I would draw it. Each of these represents a battery or a capacitor. Okay, that's how I draw them in diagrams, in circuitry diagrams. Okay? Now, in parallel, it looks like this. This is what we refer to as the ground. Okay? That's where the electrons flow to. Okay, that's the ground for it. These are connected in series. Now, let's use the analogy that I used earlier. How many of you have seen the icicles now? The icicle Christmas lights.
Oh, yeah.
The strings, right? When one of those burns out, the rest keep going. Correct? So even if one light bulb burns out, the rest of them are still going to go. Now, why is that? Because there's alternative routes for the current to flow. There's alternative routes for the electrons to flow. So if this guy burns out, all right, so the electrons are flowing from here down through to here. They can go this way, they can go this way, they can go this way, and down and down and down. They would come back together, they would meet up, and you'd have the total amount of current would come to right here. The total amount of electrons would come back together here. Now, they have alternative routes to go. So if this one burnt out, you still have two other routes in which they can go. So if you're to connect 3 batteries in parallel, and one of the batteries goes, you're still going to get a little bit of current drawing from it, okay? Because it will bypass the one that it doesn't work. Now, my example that I use for this, okay, for connecting, obviously, is those icicle lights. But how many of you have seen, some of you probably haven't looked, some of you probably don't play golf, but if you golf, the electric golf cart, all right, there's 6 batteries in the electric golf cart, correct? They're connected in series. Once one of those batteries goes, you have to test all of them to find out which one it is, because you're going to have to replace at least one. All right? It will not operate because they're connected in series. Now, if you could think of a way to connect them such that they were parallel.
They'd all have to go before the cart was shut down.
Exactly. They would all have to go before the cart was shut down. Now, you wouldn't have the same amount of power if one of the batteries went, because it's not drawing the same amount of voltage from it. But it would still work. It would still operate. But that's not what happens. They connect the batteries in series. All right. So, going back to properties again. Now, the current, the electrons, not the current, but the charges, the electrons and charges we talked about the other day, they have alternative ways to go. So to calculate how much current or how much charge you have total is I go Q1 plus Q2 plus Q3. I find out how much charge, how much Q is going through this guy, and I find out how much Q is going through here, and how much Q is going through there. Well, these are 3 separate capacitors. Okay? And each one of these capacitors has an amount of capacitance, has an amount of charge, and an amount of voltage. When we have connected in parallel, the voltages on all 3 are the same. So if I have 3 9-volt batteries hooked up, all I can produce is 9 volts total. But if one of them goes, and I still only have 2 batteries, I still have 9 volts. And if 2 of them go, I still have 9 volts. All right? Because they're connected in parallel. The total capacitance is just simply the sum of the individual capacitance. I just add the capacitance together on each.
If they were in circuit, there'd be 27. Right?
That's right.
And then
In series. In series.
Or
That's
yeah.
correct. Yeah. Okay? So all this is, we don't spend a lot of time on it in this right now, but it's the introduction you need to go into the start of grade 12. And the first thing we do in grade 12 is we refresh this. Okay? Because then we get into circuits, and then like I say, we get into electromagnetism, power, energy, all of that. So what I need for you right now, or what I suggest for you right now, is copy these 2 sheets down now and just set them in. And then I'm going to show you the process by which we solve these, which is a very precise process that I want you to use and get to know because it makes your life so much easier in grade 12. All right? Now, it is on your formula sheet. For the record, it's at the bottom of your formula sheet, but copying it down just means you're reinforcing what I just talked to you about.
All right.
Okay, we all got that done?
Yeah.
Okay,
You want to swap the other part now?
this one right here.
Copy that down too.
Yeah, let's put that in there right now. So the easiest way to do these questions, you'll get 2 of them on the test, you get 2 of them on the exam. It's 8 of the easiest marks you could possibly get. Because all you're using is this. C equals Q over V. Okay? Okay. Have a look at page 406. Flip to 406. So I want you to read this with me. 3 capacitors have capacitances of 0.2 microfarads, 0.3 microfarads, and 0.5 microfarads. If they are connected in parallel and charged to a potential difference of 100 volts, what is the charge on each capacitor? Okay, so let's talk about what we just read here. I have
Would you find like the average of the three?
Nope. That's why I use those properties I just gave you. Okay? So, first things first. They're connected in parallel. So the first thing I identify is my electron flow. Is there only one path for them to flow, or are there multiple paths for them to flow? Multiple. That means that the charge is not the same on each of those capacitors. So that's one thing I want to know. The second thing is, when I look at my characteristics or my properties, my voltage, when in parallel, remains constant. The voltage is the same for all. So here's how this works. I have 0.2, 0.3, and 0.5 microfarads. So 0.2 microfarads, 0.3 microfarads, and 0.5 microfarads. Just like that. Now, this is the one case in which I don't have to change micro to farads or microcoulombs to coulombs, okay? Because I'm just going to consistently use it. All right, it says, if they are connected in parallel and charged to a potential difference of 100 volts. So, looking at my properties, what does that tell me when it's in parallel? What about the voltage? Stays the same. So each of these has 100 volts, right? And the total on them is 100 volts. So far, so good? Okay, pencils down. I'll leave it on the board for you to copy. I'll leave it up there again to copy. All right. So I'm looking at these now. I want to find the charge on each of these, Q1, Q2, and Q3. Well, I have 2 pieces of information. I need the third. So I'm looking for charge. So how do I find Q?
Q is equal to C multiplied by V.
C times V. So I take 100 and I times it by 0.2. So I get 20 microcoulombs. I get 30 microcoulombs. I get 50 microcoulombs. And how do I find my total coulombs? Add them together. 20 and 30 make? 20 and 30 add together to give me what? 50. 50 and 50 make? So 100 microcoulombs. Now look at this. How do I find my capacitance? How do I find my capacitance in parallel? My total?
You add them.
I add them together. 0.2 and 0.3 make 0.5. 0.5 and 0.5 make 1. If I take Q and divide it by V, I take Q, which is 100 microcoulombs, and I divide it by 100 100 volts. What do I also end up with? 1. I can guarantee every time that this chart will always be right. It's very easy. Now, some might usually say, well, why do I need this chart? The reason I show you the chart is because when we do electric circuits, we don't have just 3 resistances. We have 10 or 12 resistances. So I make the chart now to get used to it, so that when I do it in grade 12, I have all my resistances down, and I use, instead of C, Q, and V, I use V, I, and R, and I do the same thing. So it's just to make your life a little bit simpler as we go. All right? Okay, now, the second one, now you're reading this question, Okay, so it says, what is the charge in each capacitor? Well, I already showed it on the chart, so that's all I need when I ask you for that in the answer. As long as you fill your chart in, you don't have to put anything else down. What is the total charge required? 100 microcoulombs, right? Got it down. Easy enough. If these three capacitors are discharged, then connected in series, and a charge of plus 30 microcoulombs is transferred to the ungrounded terminal, what potential difference appears? Okay, so now we're going to take these three batteries apart. They're no longer in parallel. Now, I'm going to put them together, and the capacitance doesn't change on them because they're the same three batteries, or the same three capacitors. Again, I shouldn't say batteries, same three capacitors. They store charges, so they have the same C on them, right? Okay, I'll come back to that guy in a second. So now I do this again. C, Q, V, C1, C2, C3, C total.
Now we're doing it for a series.
So now I'm doing it for a series. That's exactly right, Rob. Do this. My capacitance doesn't change, so I still have 0.2 microfarads, 0.3 microfarads, and 0.5 microfarads. So I've got a second chart.
Volts don't change either.
The volts are not the same in this question.
Except the total is.
The volts are not the same in this question because I've taken them apart. Now what have I done? What have I made constant now? What stays constant now? What doesn't change? Coulombs. My Q doesn't change now. And it gave you the Q. It said it's a plus 30 microcoulombs. So I put that in here. 30 microcoulombs, 30 microcoulombs, 30 microcoulombs, and 30 microcoulombs. So far, so good.
So now you go.
So I've got C equals Q over V. So how do I get V?
Q divided by C.
Q divided by C. So take 30 and divide it by 0.2. What do you get?
150.
150 volts. 30 divided by 0.3. 100 volts. 30 divided by 0.5. 60 volts. And when they're in series, how do I get my total voltage?
310.
310. I add them together. There. And to get CT, I can either go 1 over 0.2 plus 1 over 0.3 plus 1 over 0.5 and take 1 over the answer, or take 310 and 30. So I take 30 divided by 310, which gives me my answer, which is what? 30 divided by 310. Calculators?
.097.
0.097 microfarads. Et voila. There's my two charts. This one is for parallel. This one is for series.
Are we ready both of you then?
And you should write them, fill in the two charts now. So, what stays constant in parallel?
Your charge and volts.
No,
No, just your volts.
just my volts.
And then
What stays constant in series?
your coulomb.
Your coulombs, your charge. As long as you remember that, again, you can't get this wrong. And you can check your answer chart. Each of these two pieces is 8 marks. It'll be on your test, it'll be on your exam. Excuse me. Yes, sorry.
Will they have more charges on the test than the exam? Like more than
No.
3? Okay.
The hard part's honestly reading